Two microwave sources A and B are in phase with one another. They emit waves of equal amplitude and of wavelength 30 millimeters. They are placed 140 mm apart and at a distance 810 mm from a line OP along which the detector is moved. Using Pythagoras theorem, it can be shown that the distance AP from A to P is 923.7 millimeters. Calculate the number of wavelengths between source A and P. So we are given that 30 millimeters corresponds to one wavelength. Therefore, 923.7 millimeters will correspond to 30.79 wavelengths. Show that there are 33.3 wavelengths between source B and P. Now, using Pythagoras theorem, the distance between B and P is given as 998.577 millimeters. Therefore, the number of wavelengths will be 33.3. State what intensity of microwaves will be received by the detector at P. The path difference is 2.5 wavelength. So one wavelength corresponds to 2 pi radian. Therefore, 2.5 wavelength is 5 radians. Now, phase difference is normally quoted as a number between 0 and 2 pi. 2 pi is 360 degrees. Therefore, 5 pi is 2 revolutions plus pi radian. So we say that the phase difference is pi radian. And we therefore have destructive interference because they are antiphase, and therefore the intensity is 0. Describe how the intensity of reception varies as the detector is moved from P to O on the central axis. Now from P we are moving down, so we will see a 0 intensity at P. The detector will detect a high intensity, a second order maxima, followed by a 0 intensity, then another high intensity which corresponds to the first order maxima, then a 0 intensity, and finally ending with a high intensity at O.